Hi, my name is Chloe Meyer, and I'm going to be giving you an introduction to simple harmonic motion in ideal springs. I'm a speech and physics student, and I'm going to be starting off with what an ideal spring is, what simple harmonic motion is, and how that can be translated into daily life using an equation and illustrating it conceptually. What is an ideal spring? An ideal spring is going to be non-damped. It's not going to be affected by friction, which means that there's not going to be internal forces that are going to be causing the energy to decrease in that spring. So it's going to be moving forever, which is not going to happen in real life, but it's just for the sake of this presentation and for physics. It's going to be completely linear. So what that means is there's not going to be any deviation from point. It's going to be moving on a straight line, because whenever you have non-linear motion, it's going to be rotational, and that's a bit complicated for what we're doing today. It's going to obey Hooke's law. Hooke's law just defines that the amount of force that you put on a spring is going to be proportional to the amount of distance that it's going to travel, given a certain spring constant. So the more force that you apply to a spring, the greater distance it's going to travel. And we can see this in the equation F equals negative kx, where F equals force, and negative k is the spring constant, which is how tight the spring is, and x is the displacement. So the more tight the string is, the greater the spring constant is going to be, and the harder it is going to be to move that spring the same amount of distance. So we can also use that to find it that way. So what is simple harmonic motion? Simple harmonic motion is a periodic motion where the mass is going to be moving back and forth through the equilibrium, and it's going to be having a restoring force that's going to restore it back to that equilibrium point. So whenever you're away from the equilibrium, that restoring force is going to be the amount of force that is needed to restore it back to the equilibrium point. And as you can see here, this mass is going to be moving back through the equilibrium point to the point of most compression, back through the equilibrium point, and back to its final position where it was farthest and the spring was the most relaxed, which stretched. So as you can see here, we have the 3 points. So the amplitude is going to be x or negative x. That's just going to be the greatest amount of distance in the positive and negative direction of the spring. So whenever it's at equilibrium, the velocity is going to be at its maximum. The acceleration is also going to be 0. And you might be thinking, how is the acceleration 0 if the velocity is at its maximum? Acceleration is the change in velocity, and velocity is a two-factor system. You're going to have the change in direction and the change in speed factored into acceleration. So whenever you have the greatest points of magnitude of the amplitude, which is going to be at the positive x and negative x point, it's going to be the greatest acceleration, because although the velocity is 0 at these points, because it's instantaneously stopping at one point when it's about to change direction, the acceleration is at maximum, because that's going to be the greatest change in direction, because it's going one way and then it's going the opposite direction. So you're going to have double magnitude of change in direction. And the restoring force is going to be maximum at these points of amplitude. And whenever it's at 0, which is the equilibrium, you're not going to have any restoring force, because it's already at its balance point where all forces are equal. So the equations we're going to use is to find the period. The period is just the amount of time it takes to find one oscillation. Oscillation being that back and forth that I just showed you, all the way back, all the way one time. So frequency is also the inverse of that. Frequency is going to be 1 over period, and it's going to be the amount of oscillations per amount of time. So to find period, you're going to use T, which is period, equals 2 pi square root of m over k, m being mass, k being the spring constant. So whenever you have a greater mass, you're going to have a greater period. And when you have a greater spring constant, which means a tighter spring, you're going to have more oscillations. And so that's good to understand conceptually when you're thinking about it and solving for these equations, because you can keep in mind, if the mass is going to be bigger, my period is going to be bigger. So it's going to take more time for the spring to take one oscillation if you have a greater mass. And so I hope that you learned something today about what simple harmonic motion is and how it's used in ideal springs, and you can see these every day in your life. For example, car car shock absorbers have those springs in them that decrease the amount of impact you feel, and they utilize simple harmonic motion whenever the springs move back and forth in order to keep you safe. And you can also see it in grandfather clocks, although those are pendulums, it's still a type of simple harmonic motion. Thank you.